Yeah, we're focusing on resin cements.
Exactly, the ones used for luting, basically, cementing indirect restorations, crowns, bridges, that sort of thing.
hmm And we're basing this on a specific article from the Journal of Dentistry.
Right. It looks closely at one system, set max cement, and it's still primer.
And critically, how they perform under different conditions, temperature, light, things that really matter clinically.
They absolutely do. Because ultimately, the cement's behavior affects how long that restoration actually lasts for the patient. It's fundamental stuff.
So the goal here is really to unpack what this study tells us, whether you're a clinician placing these or maybe you're on the research side developing them.
Let's start with setting time. How fast does this cement actually harden?
Well, the big factor, according to the paper, was temperature. No surprise there, really.
Much faster at body temperature at 37 Celsius compared to standard room temp, 23 C.
Significantly faster. And using the primer also gave it a boost, sped things up noticeably.
Which is good clinically, isn't it? Once it's placed, you want it to set efficiently. Helps the workflow.
Definitely. And it's worth noting all the conditions they tested were still well within the ISO standards for these dual cure materials.
Okay, so setting time is influenced by temp and primer. What about the degree of conversion, the DC?
Ah, yes, DC. So this is basically a measure of how completely the cement polymerizes, how complete that chemical reaction is.
And higher DC generally means a better, stronger, more stable material long-term in the mouth.
Precisely. And here, the primer was really the star.
The most dominant factor.
According to this study, yes, applying the primer had the biggest positive impact on achieving a higher final DC.
Temperature played a role too, though. Higher temps helped.
It did. Higher temperature also significantly increased the DC. Light curing helped a bit on the final DC, especially with the primer. But primer and temp were the main drivers.
So the best combo was primer plus that 37 degrees C temperature.
That gave the highest DC values they measured, yeah.
Okay, what about the speed of the reaction, the polymerization kinetics?
Right, how fast does it get going? This is where light exposure really shone.
Makes sense. That's the point of the curing light, right? To kickstart it quickly.
Exactly. Light had the most significant impact on accelerating the rate of reaction. Gives you that rapid, on-demand set.
But didn't they find something a bit odd with the primer here?
Yeah, a little counterintuitive. When they light cured samples with the primer, the initial reaction rate seems slightly slower than light curing without the primer.
Hmm. Any idea why?
Well, the researchers proposed it might be due to how they measured it. The technique looks at a very shallow surface layer, and maybe the primer changes things right at that immediate interface differently than in the bulk material. It's, well, it's something to consider about testing methods.
Interesting. Okay, let's talk heat. Temperature during the curing.
Yes, they tracked that too. And the main source of temperature rise wasn't actually the cement's own chemical reaction, the exothermic part.
It was the curing light.
Overwhelmingly so. The light curing unit caused temperature jumps of up to, 46 degrees Celsius increase?
Wow, that's substantial.
It really is. The cement's own reaction only added about 9 degrees C on top of that.
And while they didn't directly study pulp effects, that kind of heat certainly makes you think about potential sensitivity, doesn't it?
Absolutely. It underscores being mindful of the heat generated by powerful curing lights.
So I think there's a really critical point emerging here, especially for researchers listening,
Which is?
that doing these lab studies only at room temperature, 23 degrees C, might not give us the full picture.
Definitely not. It probably doesn't accurately reflect how these cements behave inside the mouth at, say, 32 degrees or 37 degrees C, clinically relevant temperatures.
Yeah, this study really highlights that. Future research arguably needs to incorporate these higher, more realistic temperatures.
It's a crucial point for translating lab findings to clinical reality. You need to test under the conditions where the material will actually be used.
Okay, so let's try and summarize the key clinical takeaway from this specific study on setmax.
For this system, it seems using the matched Stella primer is important.
Right. And applying the curing light, especially considering things happen faster and potentially better at body temperature. That whole combination optimizes the outcome.
It looks like that combination gives you the best shot at achieving a high degree of conversion and an efficient polymerization process under clinical conditions.
So as we wrap up this deep dive, here's maybe a final thought for you to consider.
Okay.
This study looked at one cement system, setmax and Stilla primer, and measured DC at just 30 minutes post-mix.
Right. A snapshot in time, essentially.
So what are the actual long-term clinical implications, months, years down the line? And how might other cement primer combinations stack up if you tested them the same way?
Hmm. Excellent questions. It definitely opens the door for more investigation into long-term performance and comparisons across different systems under these more realistic conditions. Something to chew on.